Thank you very much. So I would like to first thank the real organizers of this meeting, that's not including me, to organize this wonderful conference in honor of Georges. So happy birthday. I'll try not to sing on Thursday. That's not my strongest point. So I will tell you a few things about on L2-Betti numbers for subfactors, and I will basically everything I will be telling today is a joint work, ongoing joint work with Sorin Popa and Dimitri Shlyakhtenko. And the basic idea is the following. So whenever you have a subfactor in the sense of von Jones, and I will introduce this topic in a minute, it has an invariant which is of combinatorial nature. It's called the standard invariant. It has many incarnations. And for the moment, you should think of that as a kind of discrete group-like structure. And for that discrete group-like structure, we would like to define L2-cohomology and L2-Betti numbers and other cohomological theories. Now, the overview of the talk will be roughly as follows. So I will start by introducing the basic notions of subfactor theory, and then a crucial tool that comes into the picture. It will be Sorin Popa's symmetric enveloping inclusion. Now, a few of you might have heard talks by me in the recent months on this topic, and then from after the first point, actually, the focus will change quite a bit and become a bit more accessible, because all the rest of the talk will mainly focus on a very general framework where actually this cohomology theory that I will be introduced for basically arbitrary kinds of inclusions of two unfactors. So we will be in a very general setup where things should be quite easy to grasp. To define L2-Betti numbers, the first definition I will give will involve, say, a kind of bar resolution that I will introduce. Of course, that will be of no help to ever make any computation. So then I will also introduce a general cohomology theory and how you can then use that kind of general approach to make computations. So let me start by this very short introduction to subfactors, so assuming that you all know what is a two-one factor. So if you have two to-one factors sitting one into the other, then there is the notion of the Jones index, and the Jones index of n as a subfactor of m is defined as the Murray-von Neumann dimension of m when you view m as an n module. So here the basic idea is that there are very few n modules, namely basically every n module is a sum of this type of right n modules where p is a projection in n, and we call that the n dimension of this module, we declare it to be the trace of p, and then we want the dimension to be additive, and in that way all kind of n modules have a dimension. When that index is finite, we call this a finite index subfactor, and then there is the following absolutely fundamental construction to build the so-called Jones tower, and it starts by taking the orthogonal projection of the L2 completion of M onto its closed subspace L2 of n, and then what you do is you add this projection to M, and you look at the von Neumann algebra acting on this Hilbert space generated by M and this Jones projection. Now, the fundamental property, because of the index assumed to be finite, is that this new algebra, called M1, has again a canonical trace. So this means that you have again a factor with a tracial state, and this means that we have a new inclusion, M sitting in M1, so that we can continue the game. And in that way, what you build is the so-called Jones tower of consecutive finite index inclusions, all indices being the same. Now, once you have this, there is a first way to look at an invariant associated to this, namely the standard invariant, is to look at all relative commutants, namely inside Mn, you look at those operators that commute with the subalgebra Mk, so where you take k, of course, to be smaller than n. Now, since the indices are finite, this is a finite dimensional von Neumann algebra or C-star algebra, namely a multi-matrix algebra. And this means that you really have a combinatorial invariant where you have sums of matrix algebras just sitting inside in all kind of complicated ways. Now, there are several ways to give an axiomatization of what kind of invariant comes out of this. And one of these axiomatizations is Sorin Popa's notion of a lambda lattice, where he exactly said, well, if you have such a grid, say, of multi-matrix algebras, then with some additional structure involving also these projections, etc., then you call it a lambda lattice, and all lambda lattices come from subfactors and vice versa. Another axiomatization is by viewing this in another way as Von Jones's planar algebras. So that's another way to axiomatize this combinatorial invariant. Okay, now the way you should think of this is that the standard invariant is really like a discrete group structure, and I will point that out more concretely later, but not just a discrete group structure, but it's a discrete group structure that somehow is acting on M. So that's the way you should think of the data of the subfactor. And then the basic tool to define cohomology and L2 invariants will be to consider the so-called, well, a kind of corresponding cross-product construction. Now, to make this very clear, and this will be extremely basic, let me just say what's my picture of ordinary cross-product. So just a countable group acting on a 2-1 factor T. So when a countable group gamma is acting on a 2-1 factor T, the ordinary cross-product T cross gamma is built, as you all know, by generating it by the algebra T, by a group of unitaries indexed by gamma, and the relations are that the conjugation with these unitaries implements the group action on T. They, of course, respect the group law. And then there is a canonical trace. So since we are in a 2-1 factor setting, any action is, of course, trace preserving. So with the canonical trace given by this formula, so finite sums like this form a star algebra because of these commutation relations. And then once I give you the trace, there is a unique completion as a 2-1 factor again. Well, as a 2-1 factor if the action is outer. Okay, so that's the cross product. Now, why am I explicitly putting this on the slide? It's because I want to draw your attention to the following easy observation: how to recover the group action, say, from the inclusion of T in S. And the concrete way I will recover the group action from the inclusion of T in S is to say, okay, with this description, we can look at the Hilbert space L2 of S and consider L2 of S as a T bimodule. Now, if I consider L2 of S as a T bimodule, it becomes a direct sum of these T bimodules. Namely, I mean, and if on such a vector in TUG, I multiply on the left with T, I mean, it only touches here. If I multiply on the right with something in T, it jumps over and becomes here alpha G of the element. And I get in this way a direct sum decomposition of L2 of S as a direct sum of irreducible T bimodules. And you can view that the way you compose bimodules is like describing how the group product works, yeah? Okay, so I'm telling this because that's the way we will look and obtain actually the cross-product construction that comes with the subfactor. So here again, let's start with any, and I will explain the word extremal at the end of the slide. So let me start with any subfactor of finite index, and then here is an analog of this kind of cross-product. So the T, so it will be really an analog of T cross gamma. What is T? T will not be M. I mean, we have to somehow balance out things. T will be the tensor product of M and its opposite algebra. M tensor M opposite. And what is S? The first definition of S is Sorin Popa's original definition of the symmetric enveloping algebra. It might scare you away at first, so I will then give a more concrete definition. So there is an abstract characterization of this enveloping algebra S as the unique 2-1 factor that is generated by commuting copies of M and M opposite, which means that it contains this T. Yeah? The T is the unique 2-1 factor generated by commuting copies of M and M opposite. And then S contains, apart from these commuting copies of M and M opposite, it contains a single projection En, and this projection En has the property that it plays the role as the Jones projection, both for the inclusion of n in M and for the inclusion of n opposite in M opposite. Because I have the algebra M with its subalgebra n, and it respects the Jones relations with respect to En, but the same for M opposite. So that's one way to view at the symmetric enveloping algebra. Now, in this way, it's not at all clear why this should have the flavor of a cross-product construction. Now, if I will try to explain you why it does have the flavor of a cross-product construction by giving this decomposition of L2 of S as a T bimodule. So T is a subalgebra of S, and I will tell you how this L2 of S decomposes as a T bimodule. So T is M tensor M opposite, and what are the M tensor M opposite bimodules that appear inside L2 of S? Well, they are the following. So we have the Jones tower, Mn, that comes with a subfactor. Now, every Mn is an M bimodule. I mean, M is a subalgebra of Mn. Now, it's not an irreducible Mn bimodule. It's not an irreducible M bimodule, so it decomposes as a sum of irreducible M bimodules. And you take the set of all possible M bimodules that appear somewhere in the tower. That's we call it C. This is somehow like the group generated by, if you wish. So you take this set of all M bimodules that appear somewhere in the tower, you take their irreducibles, and then as a T bimodule, L2 of S is really like just the sum over all irreducibles of this T bimodule, namely each H alpha is an irreducible M bimodule, then H alpha bar is an M opposite bimodule, and then in this way you get a T bimodule. And this is really the analog of the way an ordinary cross product is L2 of S is decomposed as the sum over gamma of these copies of L2 of T UG. Okay. So we call this the symmetric enveloping inclusion, and now comes the explanation of the word extremality. For the moment you can just forget about it, but it's a crucial assumption. Extremality comes down to saying that all these M bimodules that appear in the tower have equal left and right dimension. Because I introduced the Murray von Neumann dimension, you can view things as a right M module or as a left M module, and these dimensions might differ. Now, if in a unimodular situation, if you wish, that's extremality when they always coincide, and that is reflected by the fact that S is again a trace. So that's an important assumption. Okay. Now, this symmetric enveloping inclusion is actually a particular example of something very general, namely the notion of a quasi-regular inclusion of two unfactors. So now we can go back to some more elementary notions. And let me start with the easiest. So what is regularity? If you have any inclusion of two unfactors, you call the inclusion regular. Maybe normal would be a better word, I don't know. If the normalizer of T generates S, and what is the normalizer? The normalizer is the group of all unitaries that normalize T. So that's a group of unitaries in S, and if that generates S, you say that the inclusion is regular. Now, the main example is, of course, the one of cross products, where definitely you have a regular inclusion. And the important notion for us will be the notion of quasi-regular inclusions. So what is a quasi-regular inclusion? It's any inclusion of two unfactors such that the quasi-normalizer generates S. Now, what is the quasi-normalizer? The quasi-normalizer consists of all elements in S, such that if I look at the T bimodule generated by X, and maybe I want to view it in the Hilbert space, so I take the L2 closure. So if I look at the T bimodule generated by X, then it is finitely generated both as a left T module and as a right T module. Now, in the case of the normalizer, you could take here, if X is a unitary that normalizes T, then I have just here Tx, or I have Xt. I mean, I have one-dimensional modules on both sides, of course. So that's the quasi-normalizer. Now, here are the main examples, and then the body of the talk will be about arbitrary quasi-regular inclusions. So one set of examples is all SE inclusions of subfactors. They are by construction quasi-regular. For those who are in quantum group theory, I mean, if you want to stay in a 2-1 factor setting, you'd better work with, say, discrete quantum groups of Katz type, and you make cross products with them, and that gives you this kind of quasi-regular inclusions. But then, and that's also a very nice example to keep in mind, it's to take an almost normal subgroup, lambda in gamma, and to make gamma act on a 2-1 factor, and then look at the inclusion of P cross lambda inside P cross gamma. So that's also by construction, because of the almost normality, a quasi-regular inclusion. Okay. Well, an important assumption will be to look at irreducible quasi-regular inclusions, because that will make life much easier. So what's irreducibility? It's nothing else than assuming that the relative commutant of T in S is trivial. Now here you can already see why this is such a natural assumption. If T in S is irreducible and regular, for instance, then the inclusion is nothing else than a cross product, maybe twisted by a Tukos cycle. And here it's a very easy observation how to recover the group. If you have an irreducible inclusion, you can look at a normalizer, the unitaries that normalize T, and divide them by the unitaries in T, who obviously normalize T, and that gives you the group gamma. Okay, in that particular example, the quasi-normalizer and the normalizer are one and the same thing up to a linearization that you take. And I'm telling you this because it shows you that in the irreducible regular case, this quasi-normalizer is a very canonical and nice algebra. It's like the algebraic cross product of T and gamma. It's just taking the linear span of the elements T, U, G. And the same happens if you take an irreducible quasi-regular inclusion. Then this quasi-normalizer as an algebra is very well behaved. It's, as a vector space, it's nothing else than an algebraic direct sum where each H alpha is a finitely generated T bimodule. I mean, and each of these T bimodules appears with finite multiplicity. So you have this algebra S, and S decomposes really as a sum of T bimodules that are finitely generated in all possible good ways. Okay. Well, for an arbitrary such quasi-regular and irreducible inclusion, I will give you a definition of cohomology and homology. So what is cohomology for an arbitrary quasi-regular inclusion? Well, I need coefficients, and the coefficients for the cohomology theory will be just S bimodules. So bimodules over the larger 2-1 factor S. And here is the bar resolution. So the bar resolution is quite straightforward. So what are n cochains? And cochains consist of the following. You take an n-fold tensor product of this algebra curly S, the quasi-normalizer, relative over T, and you take T bimodule maps to H. And what are the obvious derivation maps? Here we go. I mean, it's like the only thing you can write, and this gives you a well-defined co-boundary operator from n-1 cochains to n cochains, and this defines the bar resolution of my cohomology theory. So that's the definition. So the cohomology of any quasi-regular inclusion with values in any S bimodule is just the cohomology of this bar complex. Okay. So that's, of course, if you have only this, there is not much you can do with that, of course, but anyway. An important observation for later is that you immediately see that we are not really looking at arbitrary S bimodules H. Because if you look at the definition of the cochain spaces, the only part of H you see in the cochain spaces are those that, as a T bimodule, are decomposed as T bimodules that appear somewhere in taking these tensor powers. So that will come later. I mean, that's the natural class of S bimodules that you should look at in this framework. Those S bimodules that, as a T bimodule, are sums of things that can appear here, yeah? Okay, I will come back to that later. So maybe just if you want to fix your mind, what are 1 cocycles in this setting? 1 cocycles in this setting, it's nothing else than derivations from this algebra to the bimodule, yeah? So that's a very natural thing to look at. Okay, so that's abstract cohomology. in the bar resolution way. And before explaining you how you can ever compute that kind of thing, let me show you how to define the regular representation and how to define L2-Betti numbers. So still for an arbitrary irreducible quasi-regular inclusion. Yeah? So the trivial bimodule is easy to define. It's, of course, L2 of S. And the first guess for the good notion of a regular bimodule would be to look at L2 of S, tensor L2 of S over T. And let me start by that one. Because I will want to define at a certain point L2-Betti numbers, so I will define not only cohomology with values in this regular representation, but I also want to measure the dimension of the cohomology space. So I need somewhere a tracial algebra to measure dimensions of the cohomology space. And the algebra that I will use to measure dimensions is the von Neumann algebra of all operators on this Hilbert space here that commute both with the left S action and with the right S action. So call that curly M. Now, an obvious observation is, of course, that the vector 1 tensor 1, that's a canonical vector in this Hilbert space here, this canonical vector defines a necessarily faithful state on this von Neumann algebra. Faithful because, yeah, I mean, if I act with S on the left and on the right, I fill the whole Hilbert space with one tensor 1. And then the nice observation is that this functional on this abstract von Neumann algebra is a trace precisely in this unimodular case that I was saying. It's a trace exactly when the bimodules that appear in S have equal left and right dimensions. So that's under the same unimodularity assumption, you get a tracial von Neumann algebra. Okay, so that's the first good guess, but it's not good enough, because if you look at this S bimodule, you could take a next tensor product with itself, for instance, and if this would be the good regular representation, you would somehow need a kind of Fell absorption principle that if I start to take tensor powers, that it should be multiples of itself. Well, that's not yet true in general for this one, and therefore actually you have to take all tensor powers with at least 2 factors, of course. So the more universal regular bimodule is this one, where you take all these tensor powers, and then still you can perfectly well work with endomorphism von Neumann algebra. And this time it will have a weight, not a state, and again it will be a trace exactly when you are in the unimodular situation. So then everything is in place, because if I look at my cohomology theory that I defined with values in any S bimodule, so in particular for this one, well, all the operators in curly M, they commute with the S bimodule structure here. So these cohomology spaces become modules over that von Neumann algebra. So they have an M dimension. And that M dimension is the definition of the L2-Betti number of the quasi-regular inclusion. So every quasi-regular inclusion has, under the unimodularity assumption, a sequence of L2-Betti numbers. Okay, as such, of course, it's completely uncomputable, but before explaining you how you can compute it, let me connect to Gaboriau's L2-Betti numbers for equivalence relations. They can somehow be obtained as a special case of this theory, except, of course, that I should then explain you the full generality setup. So what's the link with equivalence relations? So equivalence relations give rise to Cartan subalgebras. So what is a Cartan subalgebra? It's a 2-1 factor with a maximal abelian subalgebra that is regular. And maximal abelianness means that the relative commutant of A in M is A. So if you think now back at our irreducibility assumption, that was rather an inclusion of 2-1 factors with trivial relative commutant. Of course, the good intersection, and now I'm shifting, I will explain this in a minute, the good intersection of the two properties is to look at the inclusions where the relative commutant of T is the center of T. Yeah? So that's the good kind of inclusions that covers both what I was explaining before and Cartan inclusions. Well, actually, the whole cohomology theory makes perfectly sense for quasi-regular inclusions with this kind of irreducibility assumption. And then it also covers Cartan subalgebras. And to recall, I mean, an arbitrary Cartan inclusion is an inclusion of L infinity of x sitting in the algebra generated by a countable equivalence relation, probability measure preserving, may be twisted by a 2-cos cycle. And if you want to define the cohomology theory for such general quasi-regular inclusions, you have to be a bit more careful and take certain so-called rank completions with respect to the center that in the previous slides was trivial. Yeah? Okay, but then at least I would like to mention that you can do it, and that in that case, our L2-Betti numbers do specialize to the L2-Betti numbers of the equivalence relation. Now, I won't go any further into that because if you look at arbitrary quasi-regular inclusions of this with this condition, the only interesting classes are actually Cartan inclusions, where the whole theory of equivalence relations works nicely, and then subfactor irreducible inclusions, yeah, where I will now focus on for the rest of the talk. Okay, so I was saying that this cohomology for arbitrary quasi-regular inclusions, there is no way you will ever compute it using the bar resolution. So, but there is a very nice tool. And the nice tool is that to an arbitrary quasi-regular inclusion, you can associate a certain star algebra. We will call it the tube algebra, but only at the end of the talk I will explain you why we call it tube algebra. And this tube algebra will be it will look like an abstract star algebra, but the L2-cohomology and any other cohomology of the quasi-regular inclusion will become actually nothing else than a certain Hochschild cohomology of this abstract star algebra. So how to build this abstract star algebra? You start with any quasi-regular inclusion, and you first define C to be all the finite index T bimodules that appear in L2 of S. So by definition, S is a sum of T bimodules of finite index. And you take all their tensor products, so you generate, say, the group by these. You call that C. And now I will define the algebra. So it's a bit, it might scare you away at first sight. So how does the algebra look like? Whenever I have such an irreducible T bimodules I and J that appear somewhere in my construction, I will look at a vector space. I denote it as IS, Sj. And this is nothing else than the space of all intertwiners, if you wish, all T bimodule maps from the tensor product on the right, namely S tensor J, to the tensor product on the left, I tensor S. Now, I only want things to be really algebraic, so I want them to be finite rank in the sense that S is a sum of finite index T bimodules. I only want them to act actually on finitely many somehow, yeah? On a finite index subthing of S, and range on a finite index subthing of S. Okay, now I have to define a product, and the product will be so that I can take the product of something in ISSK can be taken as a product with something in KSSJ, and the result lies in ISSJ. And how does it go? Well, if V intertwines between two such T bimodules and W in the same way, then V tensor 1 tensor W, where is V tensor 1 tensor W? This one now intertwines between a triple tensor product, namely between the tensor product of S, S, and J to the tensor product of I, S, and S. And now you use the multiplication map. So multiplication in my algebra, so I'm using the ambient algebra structure. Multiplication in the algebra is a T bimodule map in this way. It's of course not bounded on the Hilbert space. So a priori this adjoint on the Hilbert space level is not well defined, but everything is somehow supported on finitely many whatever, so that makes things bounded and makes the product well defined. And you also have an adjoint operation. It's not just taking the adjoint, yeah, because the Hermitian adjoint would not land in the correct space. You have to correct with something. But as a result, and that's the only thing you keep in mind, you do associate with an arbitrary irreducible quasi-regular inclusion, you associate some abstract star algebra. And if you look well at this construction, it comes with canonical projections. I mean, that's the way, I mean, I had to touch a K with a K. So it comes with canonical projections pi, so that if I cut A with pi on the left, pj on the right, I get this vector space here. So this is just an abstract star algebra that you associate with any quasi-regular inclusion. Okay, now why is this nice? Well, the good notion of S-bimodule to look at, if you start with a quasi-regular inclusion, is to look at all. You start by, again, calling C the family of all bimodules that appear in L2 of S and their tensor powers. And now I will explain you the link between bimodules for S and representations of this tube algebra. So the very nice canonical thing that happens is the following. There is a natural bijection between Hilbert S bimodules that, when you consider them as a T bimodule, they are a sum of things that I already had. And on the other hand, non-degenerate, I will explain it to you, Hilbert A modules. So I have this abstract star algebra, and S bimodules, Hilbert S bimodules of the right nature, are in one-to-one correspondence with Hilbert space representations of this star algebra. Okay, so it's right for conventions, right A modules. This is, of course, the non-degeneracy assumption. And the other remark to make is that, yeah, since you have an abstract star algebra, you might wonder what do you exactly call a Hilbert space representation, yeah? But the star algebra is extremely well behaved in the sense that even if you're just given a star representation on a pre-Hilbert space, then it's already automatically by bounded operators. And it's really behaving in the same way as the group algebra of a group gamma, where you have the same phenomenon, of course. Defining a unitary representation of gamma or a star representation of C gamma, that's exactly the same thing. So you have this very well-behaved star algebra A, and looking at Hilbert space realizations of A is exactly the same as looking at S bimodules H of the right nature. Okay, for S bimodules of this nature, I defined cohomology, and in particular L2-cohomology. So I will have to say what it means in terms of this star algebra A, and then we will get our computational tool. Okay, in particular, there is the trivial S bimodule, L2 of S. This gives me, I won't write it explicitly, but then it can be explicitly written, a trivial A module. It's not of dimension 1. I mean, it's not just a character, but there is a trivial A module, ER. And the theorem is the following. Under this natural bijection between S bimodules of the good nature and representations of this tube algebra, there is just there is a natural isomorphism between our cohomology theory as I defined it and an Ext functor. So this is a right A module. This is also a right A module. And so this is well defined. And I didn't define you homology, but you can somehow imagine that with the same kind of bar complex notation, you can define homology. And then this is nothing else than the Tor. Now, it's a real pity that Sorin has some delay, because when we started working on this, Sorin had a big fear. And his big fear was that all of a sudden somewhere Tor and Ext would appear. And I shared the same fear because it's something I didn't know and didn't, feel familiar with. But in the end, I mean, maybe there are other people in this room with the same fear. In the end, it's very easy, of course. This is only saying that if we have this trivial A module E, and when you take any resolution of E by projective A modules, that this gives you a tool to compute the homology or cohomology of our inclusion. Yeah? So that's really all what it's saying. Okay, there was this notion K0. I mean, we want to restrict the K module, the A module K, to something algebraic. I mean, really this linear span where you cut with your canonical idempotents. Okay, so cohomology, homology correspond to Tor and Ext functors for a canonical star algebra. So now we can start to compute things. And in particular, I can reinterpret the regular representation. So not only we had this abstract star algebra, but the abstract star algebra comes actually with the canonical trace. So the star algebra has a natural positive functional. It's, again, exactly tracial in the case where you had this unimodularity assumption. And so you can make a Hilbert space, and you can make a von Neumann algebra that comes with it. And then on that one, you extend to a weight or a normal trace on that one. And here are now the regular representations. So to any S by modules are in one-to-one correspondence with A modules, and this S by module corresponds to this right A module. So A came with all these projections pi labeled by the irreducible T by modules, in particular this P epsilon projection. And then this one corresponds to a multiple of really L2 of A. And so here you also get the feeling that this is the more regular regular representation than this one, yeah? Anyway. Okay. So since we can now compute things, we can start to look at certain cases. For instance, look at amenable inclusions. So that was an important test case for us. If you have quasi-regular inclusions that happen to be amenable in the correct way that I will explain to you, then these Betti numbers should vanish. Otherwise, the theory would not be very well developed. Okay, so for that, I need a notion of strong amenability for quasi-regular inclusions. And actually, a quasi-regular inclusion, irreducible, comes with a Cayley graph. So let me define you the Cayley graph of an arbitrary quasi-regular inclusion. And it goes as follows. So you can decompose L2 of S as irreducible T by modules as a sum. And the isomorphism classes of all these T by modules that appear here, you call them V. They will be the vertices in my graph. I fix a finite and symmetric for taking the adjoint subset of T by modules. That will be the role of the generating set in the group. And how will I define now a graph? Well, I put an edge between two vertices alpha and beta, even only if the following holds. If there exists a gamma in G, and now I would like to say that gamma alpha equals beta. Now, gamma alpha equals beta does not make too much sense, but what I mean is that I can find in L2 of S a bimodule of the type alpha, an H alpha, a bimodule of the type H gamma, such that their product in S is not orthogonal to a bimodule of the type H beta. Now, it's not only a graph, it's a weighted graph, because every vertex has a natural weight that's expressed in terms of both the dimension of the module and its multiplicity, which is always finite, in L2 of S. So I get a weighted graph, and then the notion of strong amenability is just the right isoperimetric inequality for this weighted graph. So you call the inclusion strongly amenable if for every finite symmetric subset, so for every choice of generators, if you wish, and for every epsilon, you can find a set of vertices such that the measure of the boundary, because we want to look at it as a weighted graph, yeah? So you weight every vertex with this measure. If the weight of the boundary of that set is strictly smaller than epsilon times the weight of the set itself. And
as generators, is there a condition when they should really be considered generators?
Here it doesn't matter because it's really, you can make it sense of that, yeah, absolutely. And then it would really mean nothing else than taking inside S, you take all bimodules that are of the type in G, and then they should just generate S as an algebra, yeah? As a von Neumann algebra. That's all. And then the theorem works. So if you have a strongly amenable inclusion, unimodular, then all Betti numbers vanish. So that's already a good sign that the theory works. Here is another good sign that the theory works, because there are very easy notions for arbitrary quasi-regular inclusions to take free products and tensor products. Namely, if I start with two irreducible quasi-regular inclusions with the same T, then I can build a new quasi-regular inclusion. Namely, I can take the amalgamated free product in the sense of Voiculescu and Popa of S1 and S2 amalgamated over T. Now that's always automatically quasi-regular. It's not always automatically irreducible. Now if it's still irreducible, then the formula, and here, I mean, the formulas that you expect hold. I could have written it like that, yeah? So exactly like with groups, beta 1 of the free product becomes 1 plus, and then I would like to write beta 1 plus beta 1, except that you have to correct with the beta 0 if, yeah, exactly like the same formula with L2-Betti numbers for free product groups, yeah? And then for n at least 2, they are just additive. So that's again another sign that the theory works as it should. Tensor products the same. There are no extra conditions. If you have two irreducible quasi-regular inclusions, the tensor products are just a new irreducible quasi-regular inclusion, and their L2 invariants satisfy the QNet formula in the way they should. Okay, so these are still, say, classical constructions. So let me now go back to subfactors, because that was our initial motivation, and take two of the easiest families of subfactors that we know, namely the temporally Lieb-Jones subfactors and variants of it. So just as a notation, I will define the end L2-Betti number of a subfactor to be the end Betti number of the associated symmetric enveloping algebra that Sorin Popa considered. Yeah. Okay, so what are temporally Lieb-Jones subfactors? Well, you remember the Jones tower to be constructed by adding Jones projections at every stage, and then by construction, in these relative commutants, you have the Jones projections. So the Jones projections EI, they lie by construction always in these relative commutants if the indices respect these bounds. Now, if the relative commutants are as small as possible, namely generated by these Jones projections, then you say that the subfactor is a temporally Lieb-Jones subfactor at the given index. So then the next theorem that we proved is that if you take such a temporally Lieb-Jones subfactor, then all Betti numbers vanish. And well, what happens with the zeroth Betti number, I didn't tell you, but that's another sign that the theory works, because the zeroth Betti number is just the inverse of the index. So if you take, usually you have infinite index inclusions, and then it's 0. Yeah? Here is the other nice example. So what are the Fuchs-Catalan subfactors? These are somehow the subfactors with the standard invariant being as small as possible, but with the extra thing that there is an intermediate subfactor. So if you have a subfactor P sitting in between n and m, then the relative commutants become slightly larger, because you do have the projection on P that will be extra in the relative commutants. And well, if that's the only thing you get extra, then you call it a Fuchs-Catalan subfactor. And in the terminology of Bijan-Jones, this is the free composition of two subfactors. And therefore, I mean, the freeness there and the freeness in our previous things, they fit nicely together. And for Fuchs-Catalan subfactors, you get the first Betti number positive and the other Betti numbers 0. Okay, in the remaining 5 minutes, I will try to make a few concluding remarks. So here is the first thing. Let me give you some indication where this name tube algebra and our motivation came from. So what I explained to you is the following, that for any quasi-regular inclusion, there is a tube algebra. So in particular, there is a tube algebra for the SE inclusion of a subfactor. Now, for the SE inclusion of a subfactor, for those who know, this is actually nothing else, up to Morita equivalence, of Ocneanus tube algebra of the subfactor. So it's not something I will explain here, but that was our motivation and our inspiration. This tube algebra of Ocneanu is something that actually only depends on the tensor category of all m bimodules that appear in the Jones tower. What I mean by that is that you really view this as a so-called rigid C-star tensor category. So it means that this tube algebra makes sense for rigid C-star tensor categories. So that was already observed also before by Ocneanu. For those who want to know, if you have an abstract rigid C-star tensor category, if you know what this means, then what is this abstract tube algebra that comes with it? Well, it comes with projections Pi, And if I cut the algebra with pi, pj, it is, as a vector space, the sum of all these spaces of intertwiners in the category. Yeah? Anyway. But this does mean that you can also use this whole framework to define L2-Betti numbers for arbitrary rigid C-star tensor categories. In particular, and that might be of interest for certain among you, it does give you a definition of L2-Betti numbers for the representation categories of compact quantum groups. Now, intuitively, these L2-Betti numbers are rather the L2-Betti numbers of the quantum double of that compact quantum group. That's the way you should think of it intuitively. Another concluding remark I would like to make is to say a few more words on representation theory. So in terms of, our representation theory was in terms of S-bimodules. You take any quasi-regular inclusion and you look at S-bimodules. Now, for subfactors, this specializes to the case of symmetric enveloping inclusions. And then there are many, many equivalent ways for subfactors to look at representation theory. So I didn't say anything basically on planar algebras, but representation theory there was probably for the first time introduced by von Jones in terms of the so-called affine annular category of a planar algebra. And then what I did last year with Sorin Popa was, but then specifically for SE, symmetric enveloping inclusions of subfactors, to define this representation theory and to define a C-star algebra completion of the fusion algebra and phrase it in these terms. And then there are many equivalent ways that came up later. So Sergei Nezhveyev and Makoto Yamashita explained it in a completely categorical way as so-called unitary half-braidings on the category C. So that's the terminology of the Drinfeld center, if you wish. And then Gauge and Corey-Jones explained it as representations of Oknianos tube algebra. And all that is somehow the motivational inspiration to do that just for arbitrary quasi-regular inclusions and to forget about this background. But what I do want to mention and emphasize, because it's very intriguing, in this kind of representation theory, you have, of course, obvious definitions for any kind of representation theoretic property. I mean, we have a star algebra with a trivial module, with a regular module, so you can start to define property T and all kind of things you want. And then there are very interesting examples, because in the case of the representation theory of a compact quantum group, they coincide with things that were studied before, namely so-called central approximation or rigidity properties for the associated discrete quantum groups. And that I want to emphasize here, because in two very interesting cases, namely in the case of SUQ2, it was shown that you get the central Hoyru property and the central complete metric approximation property. And in the case of SUQ3, it was shown that you get the central property T. So if you reinterpret that in our framework, and that's what Sorin and I did last year, is that if you build SUQ2 or PSUQ2 corresponds to the subfactors temporally Lieb-Jones, they have a non-amenable standard invariant, but with Hoyru property and complete metric approximation property, while with SUQ3 you build subfactors with the property T, standard invariant. And so that's very intriguing what is exactly behind that, and I will stop here. Thank you.
Some questions?
So in case of actions of commensurated subgroups, because you mentioned that at the beginning of your talk, can you relate your L2-Betti numbers for inclusions with the L2-Betti numbers of the associated totally disconnected groups?
Yes, exactly. So then it's equal, but there are certain normalizations that come in, and you have to make the unimodularity assumption, which
Sure.
exactly corresponds to the Schlichting completion being a unimodular group. And then this Schlichting completion has L2-Betti numbers as a locally compact group, and then these things are indeed related. Yeah, exactly.
Some other questions? No? So thanks a lot.